Okay, so this time we're going to take a look at the proof of the power rule. So, in order to discuss the proof of the power rule, we need to do a little something from beyond the course. And that thing is called binomial theorem. So, binomial theorem is how we would expand things like this. It's a binomial to an exponent. And this one here being fairly straightforward, we know that. If it was cubed, not as many people know this, but there it is, 3x squared h plus 3x h squared plus h cubed. And there's three patterns that I'd like to take a look at here. So the first is the power of x, and the power of x decreases by 1 in every term. 2, 1, 0, 3, 2, 1, 0. Second one is the power of h, and power of h increases by 1 every term. 0, 1, 2, 0, 1, 2, 3. Now, the third one is the coefficient. Now, the coefficient of each term corresponds to a couple of things. One is Pascal's triangle, and what we would do is we would look for the row of Pascal's triangle that corresponds to the exponent that we're dealing with. So here, exponent is 2, so the coefficient, so we're going to look at this row here, row 2. Here we have an exponent of 3, so we're going to look at here an exponent of whatever row the third one is. So if we start at 0, then we would have these values here for Pascal's triangle. Now this would continue, and eventually we'll have an nth row. And the nth row is going to start at n choose 0, which is 1. And the next one, you'll see here, the second value is always equal to the row number. So that's n choose 1, that'll be equal to n. And so on and so on and so on until we get to the second last. We don't actually care about any of the other ones. The second last, as you can see from 3, is also always equal to the row number. And the last one, n choose n, is going to also be equal to 1. Because the first and last numbers are 1. The second and second last numbers are always equal to the row number. And then the rest of them in the middle are a bit of a mess. Now, we're going to make use of this property here because at some point we're going to have to do an x plus h to the n expansion very quickly here. So if we define f of x as being some x to the n, then f prime of x is going to be equal to the limit as h goes to 0 of x plus h to the n minus x to the n over h. Now, here's where we have to do that expansion. We're going to do this expansion here, and I'm just going to move this over because this line takes a lot of space. So we're going to go ahead and expand this. The first term is going to be x to the n. The second term is going to have an x to the n minus 1. We're subtracting that. It's going to have we're going to increase the exponent on h by 1. And we're going to have a coefficient in here of n choose 1. Okay, and in the next line, I'll clean that up and I'll make it equal to n. But in the next term here, just for the sake of argument, that we're going to have an x squared, to the n minus 2, we're going to have an h squared, and over here we're going to have an n choose 2. Now this is going to continue all the way down. I'll just do the second last term in this expansion because there's n plus 1 terms here, so since we don't know what n is and we don't want to put a value on it, we're just going to keep on expanding. It'll have a second last term, and its second last term will be n choose n minus 1 times x to the 1 times h to the n minus 1. And the last term will be h to the n. It always starts and ends with the term to the n. And then at the very end of all that, we can't forget that we're going to have a minus x to the n. And all of that is going to be over, ugly line there, all over h. Now, we can do one thing right off the top, is we have an x to the n, we have an x to the n that cancel there. Okay, so those go away. Now, limit as h goes to 0. Every one of these terms that is left has an h in it. So we're going to factor that h. And when we factor that h, here, we're going to have an n choose 1 times x to the n minus 1. Plus, the next term would be n choose 2 times x to the n minus 2 times h to the 1, because we factored one of those h's out, plus, and so on. We're going to have an n choose n minus 1 times x to the 1 times h to the n minus 2, and our last term is going to be h to the n minus 1. We'll close that bracket. All of that is over h. Okay? Those h's then divide out. Now, our next term, limit as h goes to 0, is going to be n choose 1. That's equal to n, because the second term in Pascal's triangle is always equal to the n value. So when it's n equals 1, it's 1. When it's n equals 2, the second value is 2. When it's n equals 3, the second value is always 3. So that's n times x to the n minus 1 plus all of these terms that are left still have some amount of h's in them. So we're going to have this x to the n minus 2 times h plus so on and so on and so on, all the way to the very last term. I don't actually need the second last term, so I'm just not going to write it. Okay? And it's not over h anymore. Now, there's nothing preventing me from examining this limit now. So I'm just going to examine this limit. As h goes to 0, this term is not affected. But now I've got something times 0, plus a whole bunch of zeros, and this last term is also going to be 0. So all of these terms are going to go and turn into 0. And all I'm going to have at the very end is n times x to the n minus 1. And that's my derivative. And that's my proof of power rule.
Thank you.